about experimental investigations I've carried out where I'm looking at the propulsive performance in the wakes of a series of bio-inspired pitching panels. So recently, engineers working on the designs of swimming and flying vehicles have looked at nature for motivation and insight, with the hopes that some of these bio-inspired designs may prove useful, especially for applications that rely on unmanned underwater vehicles. And shown here are just two quick examples of some of these bio-inspired designs. You have a tuna-like vehicle produced by Boston Engineering, as well as a bio-inspired design that relies on various pitching and heaving foils that was built by the Naval Undersea Warfare Center. So why might engineers be interested in looking at animal swimming for insight and motivation? Well, anyone who's looked at animals swimming in water, has probably noticed that these animals can move with ease, beauty, grace, and these are all things that we would associate with being characteristic of high performance. There are very few, if any, underwater vehicles that can replicate behaviors like those shown in this video here, where you have a swimming dolphin comfortably playing in swimming along waves. We have other examples like a salmon, which can effectively navigate complex currents and flow fields. And also another canonical example is a tuna, which can traverse miles and miles of open ocean with relatively high speeds and high performance. So these swimming animals, some of them provide thrust primarily with a caudal fin or a fluke that is located at the rear of the swimming animal. So in fish, this caudal fin is located shown here at the rear of the animal, and the analogous propulsive appendage is a fluke when it comes to the swimming mammals like dolphins and whales. And in nature, these caudal fins and flukes display wide variation in planform geometry. I've shown here a few abstractions of some of the shapes you might see in nature. And typically, when we think of what is characteristic of a high performance swimmer, we envision a lunate or a forked propulsor that has a large aspect ratio. So going forward in this talk, I'm going to focus on three of the shape abstractions shown here. The first is a forked planform where the trailing edge inflects inwards. The second is what's called a truncate planform, which is just like a trapezoid. It has a straight or vertical trailing edge. And then the third is a pointed planform where the trailing edge inflects outwards. Now, with these three shapes that I've highlighted here, I want to explore their wakes and their propulsive performance using these simplified experimental models in a recirculating water tunnel. And these simplistic or simplified experimental models in these water tunnels are useful because that way we can parameterize how we study bio-inspired propulsion. So if you begin with something like a simplified propulsor geometry shown here, you can systematically vary some of the variables I've shown, like leading edge and trailing edge sweep, leading edge length, trailing edge span, mid-span chord length, things like that. And you can understand some of the roles that planform shape and aspect ratio play in terms of propulsive performance and, say, wake behaviors. You can also systematically vary things like kinematics. So you can inject various pitching and heaving motions into your motion profiles and see how those things impact bio-inspired propulsion. And then you also have control over the material properties that you're using for your propulsors. And going forward, I'm only focusing on rigid material properties. So using some simplified experimental models that are meant to represent biology, this talk seeks to understand some of the relationships between planform shape and trailing edge shape, motion kinematics, propulsive performance, and then the resulting wake behaviors. And going forward in this talk, I'm going to focus on kind of three overarching major conclusions. The first of those is that some of these experiments on isolated rigid propulsors may not provide accurate representations of animal swimming. And what I mean by that is when you study these propulsors in isolation, you may end up seeing some propulsive performance results that are a little bit counterintuitive given what you may expect from observations of nature. And what I mean by that is that these low aspect ratio pointed propulsors always seem to perform better. I'm also going to talk about how planform shape and motion kinematics tend to have little qualitative impact on time varying performance and time varying forces, despite the fact that they have significant quantitative impact. And then when I talk about some of the wakes these bio-inspired propulsors produce, I want to focus on how two-dimensional simplistic descriptions of the wakes of these bio-inspired propulsors really fail to capture important wake dynamics. Things like changes to planform and straddle number have significant impact on wake structure and topology. So I mentioned earlier that I focus on simplified experimental models, and shown here on this slide are the 5 planform shapes that I'm going to talk about going forward in this talk. So I have 2 scale schematics shown of all 5, as well as some descriptions of the geometric parameters. So going forward, as I mentioned the panel number, so panels 1 through 5, you can think of panel 1 as being of the highest aspect ratio and the most forked trailing edge, and then panel 5 as being the most pointed panel with the lowest aspect ratio. So as panel number goes up, the trailing edge becomes more pointed and the aspect ratio decreases. So first I want to talk about how do these 5 planforms perform when I'm looking at experiments that involve pure pitch in a recirculating water tunnel. So in order to study the mean and time varying performance of these panels, I used a Mini 40 force torque transducer and collected measurements for 25 total straddle numbers. So each of those 5 panels shown on the previous slide had 5 different pitching amplitudes. And then I studied their propulsive performance, and then I will talk about that going forward. So each of these panels were pitched about their leading edge through 5 different angular amplitudes. This is only a pure pitch experiment involving a sinusoidal set of kinematics. And as I mentioned on the earlier slide, each of the 5 panels resulted in 5 unique straddle numbers that are shown here. They range from 0.09 to 0.66. So this straddle number range captures the straddle number range of actual animal swimmers, as well as straddle numbers outside of that range. And one thing I want to point out on this slide is the fact that when I'm talking about straddle number in this presentation, I have to use an average trailing edge amplitude for that value of A in the numerator for my straddle number calculations. And this is just due to the fact that as the trailing edge varies across the span, the trailing edge amplitude also varies. So I use an amplitude based on the entire span of the panel. So with respect to mean propulsive performance, these experiments show that the best overall performance in a mean sense is displayed by the most pointed panels of the lowest aspect ratio. So mean thrust increases as the panel number increases, so as the trailing edge becomes more pointed, and aspect ratio decreases, while all the forked panels that I studied failed to actually generate a positive thrust. And similar results are observed for efficiency, where if you're looking to pitch with the highest efficiency, you want to use a lower aspect ratio, more pointed panel. So ultimately, decreases in aspect ratio are actually associated with increases and improvements in propulsive performance. So that's just a discussion of some of the mean performance results. I also want to talk about how do changes to planform shape and straddle number impact the time varying forces, not just the mean forces. And before I go into that, I just want to reintroduce the kinematics of the panels. So all panels were pitched according to a sinusoidal motion profile, and shown here is a non-dimensional time period for one cycle of motion. So at a time of 0, the panel is in line with the free stream flow, and it is beginning to pitch in a counterclockwise fashion until it reaches a motion extreme a quarter of the way through a pitching cycle, before returning ultimately back to alignment with the free stream flow, and then reaching a second motion extreme. And I'm going to kind of focus on the 4 timings and the things that occur around these 4 timing events that I've just shown on this slide. So ultimately, changes to planform shape and straddle number result in qualitatively similar traces for the time varying coefficient of thrust. And what I mean by that is that even though you're changing planform and straddle number, the key timings in the forces are relatively unaffected. So regardless of the planform shape or the straddle number, thrust tends to peak as the panel retreats from motion extreme. And this is observed elsewhere in the literature too, even for rectangular panels and things like that. and the thrust minima always tend to occur right after the panel crosses the wake center line, each occurring about 1/8 of a period after either the motion extreme or alignment with the free stream flow. And shown here, I can highlight the 2 instances where thrust reaches a minimum in the cycle. And despite the fact that the qualitative timings of these forces are relatively unaffected by changes to Stroll number and planform shape, you do get significant quantitative changes in the time-varying coefficient of thrust. So shown here are just 2 plots showing panels 1, 3, and 5. Again, panel 1 being that most forked panel, panel 3 being a trapezoidal panel with a straight showing edge, and panel 5 being the most pointed panel. So at a lower Stroll number, all of these panels reach they reach lower maximum thrust values. And also in an absolute sense, their thrust minima are much weaker. But as Stroll number increases, the thrust maximum and thrust minima also increase. So similar results are observed if we're looking at some of the side forces. People often don't look at side forces, but I do think they're useful to look at, especially if the design of an underwater vehicle is concerned with maneuverability. So as with the time-varying thrust, these time-varying side forces are qualitatively unaffected by changes to planform and Stroll number. Peak magnitude side forces always occur when the panel crosses the center line with maximum angular speed, and the near zero forces occur at motion extremes at 1/4 of a way and 3/4 away through a pitching cycle. But I don't have the y-axis fixed on these 3 graph comparisons, but the quantitative values of the maximum side forces are significantly impacted by changes to planform and Stroll number. So I just wanted to reiterate again that with respect to mean performance, decreases in aspect ratio and a more pointed trailing edge are associated with better propulsive performance. And now I want to ask questions about what is going on with the forces that are acting on the panels. And how do the different components of forces acting on the panel impact these mean performance values? And what I mean by different forces is the normal and axial components of force. So I'm adopting a methodology here from David et al., which is a paper published in 2017, where I'm going to decompose the time-varying thrust into a normal component as well as an axial component. And then I want to look at how each of these components contribute to that mean or instantaneous thrust. So basically, what are the roles of these components and how are they influenced by changes to planform and kinematics? And how might the actions of each component influence performance and explain some of those counterintuitive mean performance results that I showed earlier? So in terms of the mean time averaged axial forces, what happens is that mean axial force, regardless of the planform used, increases monotonically with Stroll number. So this is not a result that was observed with respect to mean thrust. Mean thrust actually decreased with Stroll number for the fork panels. And even though the mean axial forces increase for all panel planforms, fork panels always fail to produce a positive mean axial force. So they're unable to generate axial forces useful for propulsion. So I kind of touched on this, but that mean time average axial force scales nonlinearly with Stroll number, and this is in opposition to some of the results seen for mean thrust. So the largest mean normal forces are actually associated with the largest propulsive efficiencies, whereas the largest mean axial forces were associated with the largest mean thrusts. So peak efficiency tends to occur at a Stroll number that is near to the maxima in normal force. And as you increase Stroll number beyond this mean normal force maximum, you see a rapid decline in the normal forces. And as this rapid decline sets in, you see a increase in the mean axial forces. So if you can see on this slide, the rise and then subsequent fall in mean normal forces with Stroll number qualitatively mimics what is going on with the propulsive performance. And ultimately, I think these results show that a lot of the poor performance of fork panels in a mean sense can be explained by the significantly negative normal forces that develop on them. These fork panels always have significantly negative normal forces, even when their axial forces are close to zero and almost ready to become positive. So I think these axial forces can be used to kind of define two thrust producing regimes for the panels that do produce thrust. So the axial forces tend to dominate at larger Struhl numbers, and high axial forces define an area where mean thrust is large. But if propulsor is pitching at a relatively high efficiency, the normal forces tend to be close to their maxima, and these correspond to maxima in propulsive efficiency. And I mentioned I adopted this methodology for decomposing the forces from this David et al. Paper in 2017. And I want to point out that they were looking at a NACA 0012 airfoil pitched at relatively small pitching amplitudes. And the differentiation of these two regimes where axial forces dominated one and normal forces dominated another was not observed there. But also I did look at much larger pitching amplitudes than they did. And as pitching amplitude and Struhl number are increased, that is when you start to see this degradation in normal forces for all panel geometries studied in the current work. So that's a description of the mean performance and the time varying performance for panels operating in just pure pitch. And now I want to talk about how do changes to plan form and Struhl number influence some wake behaviors for the scenario of a purely pitching motion. So in order to study wake behaviors, I conducted a campaign of experiments where I was collecting wake velocity vectors using stereoscopic particle image velocimetry. Shown here is just a basic schematic of my SPIV setup. I had two SPIV cameras located overhead of a recirculating water tunnel, and then a horizontal laser sheet that was at a fixed location at approximately half the depth of the water tunnel. And then I used this traverse that is mounted outside the tunnel to move my entire experimental assembly up and down through this laser sheet to capture velocity vectors. These are 3-component velocity vectors in multiple planes in the wake. So shown here, it's just a little animation about how these experiments would be carried out. I would collect PIV in a single plane, move in the span-wise or vertical direction, this whole experimental apparatus upwards, and then collect more data in another plane. So ultimately, I used this method to capture 27 planes of stereoscopic PIV data for all 25 of those Struhl numbers that I introduced earlier. These planes were collected across the bottom half of the wake, and then they were mirrored about the midspan in order to construct a full volume of data. And I collected throughout the pitching cycle, phase averaged PIV data at 24 unique phases in the pitching cycle. And that was kind of a brief overview of what I did. But here are the results. So you end up with 24 phases of 3-component velocity data across a full volume for all 25 of those Struhl numbers shown earlier. And as you look at this plot, as you go, or this slide, sorry, as you go from top to bottom, these are the wakes for the most forked at the top to the most pointed at the bottom. So panel number is increasing from top to bottom. And as you go left to right, the Struhl number is increasing from the lowest pitching amplitudes to the highest pitching amplitudes. And I just want to focus on a few instances of the wakes that are shown here. I don't have time to go into all of them. So I want to first look at what happens with these volumetric wakes when Struhl number is low. So for low Struhl numbers, the wake topologies are relatively simple. What I've shown here is just panel 1, panel 3, and panel 5 at a single phase of their pitching cycle at their respective lowest Struhl numbers. And when Struhl number is low, the wakes tend to have low numbers of vortices. And one thing to point out here is that their shape matches the local trailing edge shape. So you can see the vortices inflect inwards when they're shed from panel 1, They're vertical in their orientation for panel 3, where the trailing edge is straight, and then the vortices tend to bow outwards for panel 5, where that trailing edge is pointed. And at these low Stroll numbers, you can get simplistic wake patterns, such as the 2S pattern that's evident for panel 1. But as you increase panel number, you actually see the generation of more vortices, and you can actually observe a 6S wake pattern. So as Stroll number is increased to the intermediate range, these topologies just become more complex. You actually see the onset of instability vortices. So you might see these referred to as Kelvin-Helmholtz-like instability vortices in the literature. So so the wakes can contain at least 4 like-signed span-wise vortices, and this is occurring regardless of the panel geometry. And again, as Stroll number comes to this intermediate range, regardless of panel geometry, you can see these Kelvin-Helmholtz-like instabilities form. They form for all planform shapes. This trend continues for the largest Stroll numbers, where the wake ultimately comes dominated by these instability vortices, and you can see up to 7 like-signed vortices being shed per pitching cycle. And another thing to point out here is that as the Stroll number increases, you tend to see more exaggerated wake behaviors like span-wise compression, transverse expansion of the wake structures, and you see wake breakdown where these vortex structures are torn apart. And I think these wake results show that if you're just looking at wake topology, so not necessarily the shape of the wake vortices, but how many are there and how are they connected to each other. Stroll number is more dominant than planform with respect to wake topology. So shown here, I have panel 1 and panel 5 at low, moderate, or intermediate, and high Stroll numbers. So you can see similar wake topologies among these and between these wildly different planforms. At low Stroll number, the numbers of vortices are relatively low. And then at moderate Stroll number, you end up producing about the same number of these span-wise vortices per cycle. And you can kind of reiterate this here, where even when you have cases of negative and positive thrust and variation in planform shape, similar wakes can appear by changing Stroll number, and they appear even when planform shape is changed and propulsive performance is changed significantly. And I just kind of want to summarize those results to say that, like, the volumetric wakes of these finite aspect ratio propulsors, especially when you introduce things like leading edge and trailing edge sweep, are often not simplistic. A lot of people want to try to categorize them into things like 2S and 2P wake patterns, but these descriptions may not always be sufficient. I've observed up to 14 span-wise vortices being shed during a pitching cycle, for example. And now I want to take some of these wake results a little bit further and look at whether or not connections can be made between some of the time-varying forces that I discussed earlier and some of the wake patterns. And when I say wake patterns, I mean looking at span-wise vorticity. And I'm just going to talk about a single representative case, which is panel 3, the trapezoidal panel, at its intermediate Stroll number of 0.33. But these trends are pretty consistent regardless of planform and Stroll number. So ultimately what happens is that while thrust rises during a pitching cycle from its minimum to a maximum, vorticity of a given sign, again, span-wise vorticity, is building on the panel surface. And then when thrust decreases from its maximum towards its minimum, this vorticity is being shed into the wake. And I'm going to demonstrate this by looking at a few times in the pitching cycle. So I've shown here some instances I'm going to look at labeled 1, 2, and 3, which is as thrust is increasing and as the panel pitches towards a motion extreme. Pitches away from a motion extreme after a time of maximum. Okay, sorry, I misunderstood my diagram. So we're pitching towards a motion extreme, meeting at a time 2, and then retreating from it at a time of maximum thrust. And then subsequent to that, I'm going to look at the decay in thrust as the panel crosses the wake center line and continues pitching. So at instance 1, the panel is at a minimum in thrust, and there's no positive vorticity shed into the wake. The previously generated negative vorticity is almost completely detached from the panel surface, but as you go further in the cycle, it's not really captured by my PIV, but positive vorticity is being it is developing on the advancing face of the panel, and you can start to see it shed into the wake right at the trailing edge at this third and final instant in the pitching cycle. And as you continue further and thrust decreases, the positive vorticity is shed into the wake, and this repeats again for the next half of the pitching cycle. So all the results I talked to about so far are just about pure pitching. And just to summarize them, my results show that for pure pitch, pointed panels always outperform fork panels. They do this with respect to both mean thrust and propulsive efficiency. So if you're designing an underwater vehicle and your goal is to use a purely pitching motion with high thrust and efficiency, I would recommend going with a more pointed trailing edge of reduced aspect ratio. And I also talked about how higher propulsive efficiencies are associated with larger mean normal forces, and higher mean thrusts are associated with larger mean axial forces. And I believe the poor performance of the fork panels in a mean sense is due to the fact that they are plagued by significantly negative mean normal forces. And some of my wake results showed that Struhl number is very dominant, more dominant than planform shape in terms of wake topology. So after those purely pitching experiments, I performed another set of experiments where I was looking at, can improvements be made to better represent biology, and can that resolve some of the counterintuitive findings where lower aspect ratio, more pointed panels perform better in these water tunnel experiments. So one of the improvements I wanted to make was introducing another set of kinematics. So before, I had no side-to-side heave, so I'm going to talk about some experiments that incorporate heave, while I'm also looking at the effect of pure pitch, pure heave, and then the combination of heave and pitch with an appropriate phase delay. And then for those of you that are familiar with what actually happens when an animal is swimming in nature, you'll know that when they're cruising, they're in what's called a self-propelled swimming state. So during cruising, these animals are swimming with constant speed. And given that speed is constant in a mean sense, the thrust and the drag are balanced. So the net forces should be zero. So those earlier pure pitch experiments where the free stream velocity was fixed by the tunnel setting and a positive or negative thrust was measured are not representative of how an animal might be swimming under a cruise condition. So I'm going to talk about some experiments where I'm taking those 5 previous panels and I'm just showing them here to reiterate some of their geometric parameters. And I'm looking at how these panels perform with different kinematics and how they perform with respect to self-propelled swimming speed. So I had to redesign some of my experiments where I'm looking at a pitch motor that is, again, controlling pitch about the leading edge. This is connected via a rack and pinion system to a heave motor that actuates the side-to-side heave. And then I use this single axis load cell to just measure stream-wide forces. And ultimately what I did was I varied the tunnel setting until I got a zero net force measured over a few pitching cycles on this load cell. And in order to investigate the impact of changes to kinematics on self-propelled swimming speed, I did 15 different kinematic scenarios. And they're summarized here by the kinematic parameters in this table. I had 3 cases of pure pitch, 3 cases of pure heave, and then 9 total cases where those pure pitch and pure heave amplitudes were combined with a 270-degree phase lag between pitch and heave. And this phase lag was selected based on a literature review where phase lags of this value were shown to correspond to high propulsive efficiency. And one thing I want to point out here is that actually I didn't know this a priori, but the heave amplitudes of the more pointed panels had to be reduced because when they were actually too large, they would swim too fast, and I could not raise the tunnel speed high enough. So I do have some different heave amplitudes for the forked and straight panels in comparison to the pointed panels. So I want to look at how did kinematics and how did planform influence the self-propelled swimming speed. So for the case of pure pitch, as with the prior work looking at mean thrust and mean propulsive efficiency, more pointed lower aspect ratio panels display higher self-propelled swimming speed. And this occurs even as that angular pitching amplitude is increased. These lower aspect ratio panels always swim faster. And one thing to take away from this slide is also the fact that the self-propelled swimming speed is somewhat insensitive to increases or decreases in pitching amplitude in pure pitch, at least for the pitching amplitudes I studied. However, that behavior changes when you go to pure heave. So for purely heaving motion, self-propelled swimming speed is strongly influenced by changes to heaving amplitude. You can see that for all panels except for panel 1. Increases in the heave amplitude result in significant increases in the self-propelled swimming speed. But even when these kinematics are changed, self-propelled swimming speed always is higher when the aspect ratio is lower and the trailing edge is more pointed. And this slide just illustrates how changes to heave amplitude and changes to pitch amplitude result in different behaviors with respect to the self-propelled swimming speed for these 5 panels. So to get to the most biologically accurate kinematics, I'm going to look at how do a combination of pitch and heave influence the self-propelled swimming speeds. So in order to achieve the highest self-propelled swimming speeds, as one may expect, you want to combine pitch and heave with an appropriate phase delay. So my highest overall self-propelled swimming speeds were observed for these cases of combined pitch and heave. And this is true regardless of the panel platform. So all panels boosted their swimming speed when pitch and heave were combined. And for, say, a fixed amplitude, in a fixed pitching amplitude, larger heave amplitudes always resulted in higher self-propelled swimming speeds. And even when these two kinematic sets are combined, the lower aspect ratio more pointed panels still always swim faster than high aspect ratio forked panels. And one thing I also want to point out is that self-propelled swimming speed can actually be diminished when pitching amplitude is increased. And this is something that's not observed for increases in heave amplitude. And I can show that here, where as you go from left to right on this slide, the pitching amplitude is increasing. So for example, the first plot is increasing heave amplitude while pitch amplitude is fixed at 10 degrees, and then 15 degrees, and then 20 degrees as you go left to right on this slide. So if you actually want to achieve the highest self-propelled swimming speeds, you should keep the angular pitching amplitude value to an appropriately low value. You can actually diminish your self-propelled swimming speed if you increase it too much. So to summarize some of these results that I just went over, combined pitch and heave yields the fastest self-propelled swimming speed, provided that you do maintain a small angular pitching amplitude. And regardless of the kinematics employed, the lowest aspect ratio panels always swim with the highest self-propelled swimming speed. So what is the relationship between Struhl number and self-propelled swimming speed? These experiments are a little bit different than the ones where I focused on pure pitching in a fixed velocity water tunnel experiments, in that the Struhl number now becomes an output. You don't know that a priori, and it comes out of the conditions required for zero net thrust. So for all panel geometries, swimming speed tends to decrease as the output Struhl number increases. But that being said, all panel planforms do show significant variations in the stroll numbers that result from a given set of kinematics. And there's really no observed one-to-one relationship, one-to-one relationship between swimming speed and stroll number for a given planform. And these stroll numbers I observed are in no way restricted to that range of about 0.2 to 0.4, where a lot of people have measured animals to swim. In fact, most of my stroll numbers tended to occur below and outside of that range. So one of my motivations for these swimming speed experiments was to say, can these kind of experiments explain away some of the previously observed counterintuitive pure pitch results? And ultimately, I found that they did not resolve some of the disconnects between those purely pitching results and observations of nature. So introduction of more biologically accurate kinematics, and then in my opinion, a more biologically accurate measure of propulsive performance, that being the self-propelled swimming speed, did not resolve some of the disconnects between that first set of experiments I showed and observations of nature. And one thing I want to point out here is that these results I've been showing for self-propelled swimming speed are dimensional. You can see out here, the swimming speed is given in meters per second, not something like a chord length per second, something that could be easily non-dimensionalized. So going forward, I still need to study how these results stand up to non-dimensionalization, as well as doing these sets of experiments again, where I'm focusing on doing things like maintaining a fixed aspect ratio while also varying trailing edge and or leading edge sweep. So there's a lot of variables at play, and this kind of goes back to what I was saying about why these experimental models can be useful, because I do have control over how I can systematically vary things like leading edge sweep angle, aspect ratio, and things like that. And those are all the results I wanted to talk about today. So just to summarize some of the things I have discussed in this talk, I've shown that for purely pitching isolated rigid propulsors, you may not capture accurately representations of animal swimming. They produce some counterintuitive performance results. They also have relatively low and inefficient values of propulsive efficiency, displaying the highest peak value of approximately 15 or 14%. And again, these straight panels with the straight trailing edge and a pointed trailing edge were the only ones I studied that were capable of producing positive thrust and positive propulsive efficiency. And this purely pitching set of experiments can be improved in terms of their ability to represent nature by introducing various motion kinematics that are not included in pure pitch. So in my case, that was the introduction of heave, as well as a phase delay between pitch and heave. And those findings showed that even when you do introduce more biologically accurate kinematics, there still may be a disconnect between your experimental results and the observations of nature. For the kinematics I tested, if your goal is to produce a high self-propelled swimming speed, you're still going to want to stick with a lower aspect ratio, more pointed panel. And with respect to some of the wake results I discussed, I talked about how the wakes of these finite aspect ratio bio-inspired planforms are very complex. They're highly three-dimensional. They're comprised of alternately signed vortex rings, which drive behaviors like spanwise compression and transverse expansion. And these behaviors are strongly linked to stroll number, as well as the wake topology is strongly linked to changes to stroll number. And that appears to have stroll number appears to have a bigger impact on wake topology than planform shape, but planform shape does have a significant impact on the shapes of the vortices that are being shed into the wake. So at this point, I'd like to end my talk and open the floor up for any questions.
Well, very nice presentation, Justin. So it's a very sophisticated research and you present it logically. Essentially, it's time for questions. You can just open your mic or you can raise your hand or left in the chat. Like anyone has any questions. So
can I ask a question, Kai?
For sure.
Justin, nice talk. This is Jun Zhang from NYU. We worked on some flapping flight as well over the past few years. I have a naive question. Have you thought about normalizing some of the data using the area of your flapper?
So I kind of got into this at the end. We're still, so I mean, a lot of the, at least with respect to propulsive performance, I only showed non-dimensional results for things like thrust and side forces. So there is an area component in that non-dimensionalization, but these are actually questions within our group that we've been struggling with. And we've talked to other researchers like Keith Morid at Lehigh. And I think it's not a naive question at all. It's a very good question about, with these simplified experimental models and also simulations, it's not just a question for experiments. How do you best capture and non-dimensionalize and then compare between cases when you're varying leading edge sweep, planform area, as you mentioned, aspect ratio, and then trailing edge sweep? So that was kind of a long-winded answer, but yes, we have thought about what's the best way to incorporate area in comparisons between these cases. But I do think it's a good question for the broader community, which is how do you best capture variations among planforms like this in a non-dimensional sense?
Okay, thanks.
I don't know if there's a good answer. Yeah.
Okay, I have a feeling that if you use areas, those data may collapse better from case to case, right?
Which data? Sorry, which specific? I know I showed a lot.
Maybe on page 13 or 20. I don't quite remember.
Okay. Oh, early. So yeah. So
early.
Let me.
It's very rich, by the way, your results.
You can still see my screen, right?
Yes.
Okay. Sorry, this is taking a while. So if we're just looking at the mean thrust and mean propulsive efficiency results, which I'm getting to here, I have the mathematical definitions shown on the screen here. Right. So these do capture S, the planform area. So they are non-dimensionalized by planform area. But I think again, my broader question for a lot of people just to ponder is, if you're just given an area, you don't have an idea about shape. So you don't know what the leading edge looks like. Is it curved? Is it sharp and linear? Things like that. It's a question I don't have a good answer for, but I do wonder, like, if in a lot of these parameters you need to add some sort of correction for something beyond just the planform area, but the actual shape of the planform.
Okay, thanks. Kai, I wonder if I can follow up with another comment.
Yes, for sure.
Okay. Justin, I appreciate the effort. You want to get the dimensionless number, regarding normalization. I think there's one area you can use to normalize all cases. That is the area for the fin, for the very end of the fin, sweeping through space. That's the area.
Okay, so like a swept volume.
Exactly. Yeah.
Yeah, and that would be good too, because then that would kind of like how I defined the Struhl number, where I looked at like an average trailing edge amplitude. You're capturing span-wise variation in the area there, right? Because you're having to deal with the sweeping out. So let me make a note, because that's my next set of experiments is going to be adding on to some of those self-propelled swimming speed experiments. And I need to I need to find a good parameterization for how to design those plan forms to look at kind of what you're getting at.
Let me advertise a little bit on a very a short note I wrote in 2017 for GFM. Okay. There was a focus on fluids, something like that. I probably mentioned that the swept area of the fin could be an important factor in evaluating the performance of a flapping or pitching wing.
Okay.
And, yeah, but thanks a lot, Justin. It's a very
no, and
you know, it triggered my you know, all my thoughts.
Yeah, and these are conversations me and my advisor Melissa Green have had with other people at conferences for a few years now.
Right.
And swept area is something I haven't looked at numerically yet. Like I haven't actually done the math on, so I need to do that.
Yeah, send my regards. Okay.
Okay, thank you. Yeah, thank you for the input.
Yeah. Bye-bye. Thanks.
Yeah, thanks for the question. So is anyone else has questions? So essentially, Justin, I have a question.
Okay.
I saw like say you did a very sophisticated measurements, use stereo PIV and for what like I don't quite understand how you connect all these like vortex to make it like fully 3D. But anyway, it seems like all the vortices, like the complex topology is in the far sort of like far away. Like near the panel is still sort of like vortex tubes connect. Maybe it depends on phases, but like it's to me it seems like near the panel is still sort of organized. So maybe these like complex vortices in the downstream will not like influence the thrust or the axial forces on the panel. Do you agree, or like how do you consider that?
So this kind of ties into what we were discussing in the prior talk, which is there's a paper by the prior question, sorry, not the prior talk. There's a paper from Keith Morad's group at Lehigh where they are looking, it's a recent paper. I have it floating around here somewhere, but you can email me if you want it. They looked specifically at that. They kind of want to look at how performance can be predicted for these or modeled for these more complex bio-inspired shapes. And they have a term in their performance calculations that deals with the induced flows from the vortices. And I don't have a good answer off the top of my head for like, you know, hey, is it, how close does a vortex have to be to the panel in order to contribute to some of the forces? But I suspect these vortices that I've shown here, that they're breaking down far away from the panel. Towards the end, the downstream end of my data window, they are too far to significantly impact any of the forces going on in the panel. And I think that's what you had said, correct? You had said, are you right in thinking that as these structures get very complex and broken up, they aren't really contributing to the forces, right? That's what you had said, correct?
Yeah, thanks, Justin.
Okay, yeah, so there are some recent papers looking at modeling of these though, where they do bring in terms to account for the actions of the vortices on the panel surface.
Yeah, so anyone else has questions?
Yeah, I should comment. It's Jun Zhang again. I noticed that most of the audience are from China. Is that right, Kai?
Correct, yes.
Okay, so this is third day of the big Lunar New Year, and most of the people are either half drunk or very sleepy right now. It's 11 p.m. Justin, just let you know. Yeah.
That is fine. Everyone deserves to relax every once in a while. So.
Well, it's a very nice talk. Yeah, it's very better
Well,
to
thank you.
listen. Yeah.
Not sleepy in Minneapolis.
Okay.
Oh, hi, Melissa.
Hello, Nora.
Hi, Mr. Justin.
Sometimes Nora's shy around me.
Since we're on this page 33, I just wondered another naive question. If the training end of this platform is flexible, there's a certain flexibility. Do you think one can reduce the little eddies, the number of eddies to some extent?
I suspect yes.
Okay.
At least in my head, I always view sharp corners and sharp edges as essentially vortex generating devices.
Right.
So like where there's always going to be a separated shear layer whenever you have, air quotes on always, but there will usually be a separated shear layer that rolls up into a vortex if you have a sharp edge.
Okay.
And if you get some sort of flexible edge, especially something that kind of like tapers rather than just having a sharp end, you can probably reduce some of these things. And that kind of goes back to my earlier like motivation slide, which is with experiments like this, you do have the ability to start messing around with material properties. So that's something I've never looked at here, which is how do my results change if I were to recreate these experiments in the same kinematics, but now I'm using something that's more biologically accurate with respect to flexibility. There's tons of people out there that have done PIV where they look at, say, just a single plane at the midspan for a rigid and then a more flexible and then a more flexible propulsor. And you do see variations in the wake structures. And I'm, at least in some of like the earlier, like when fluid mechanics experiments were starting to visualize flows, like there are a lot of experiments where you just drag a plate through ambient air or whatever, and you get these Kelvin-Helmholtz like roll-ups.
Right.
And I'm assuming they would diminish significantly if I had flexibility, like even just a flexible flap at the end.
Right. And then you might end up with this 2S 2P picture.
Correct.
Pictured by the Princeton groups.
Yeah.
Maybe.
And and a lot of that too is, I guess, I think some people might kind of categorize a wake into something like 2S or 2P, and you can see there's some like smaller little patches of vorticity, and you're like, well, is this a vortex or not? And I think a slide like this shows that if you start looking at a full volume of the wake, these little smaller structures that you may not have said count as a full vortex, like have a significant span-wise extent. And if you just call like a midspan wake like 2S, you might be missing some of these smaller instability vortices that are admittedly small in cross section, but they go from span-wise tip to span-wise tip. And you also may miss them if you maybe don't have extremely good resolution in your PIV. Like
I would hop in there that having seen these now in multiple cases, the fact that they persist when you interpolate across multiple planes, when you interpolate across multiple planes, and these are from all phase average PIV, and they're also there in the instantaneous PIV. Like we dug into them for a while because we were curious about them, but they definitely are persistent.
Right. Well,
yeah, and you can kind of see how if I show this slide, and I'm looking at the positive thrust case in the top right, it's kind of like, what do you want to call that vortex that's in the middle? Is that blue negative vortex? Is it 3 separate vortex cores that eventually merge together? It's kind of
I call it the colliding galaxies.
Yeah, I like that too. It's a very elegant way to phrase it. but you can, as you start seeing, if you take like a full volumetric picture of the wake, and this can be done too with CFD, you can see that these are actually like-signed vortices that are kind of like twisting around each other. And then eventually, as they get far enough downstream, they do merge together and form a more circular single vortex. But when they're close to the trailing edge, they kind of come off almost like slightly disconnected. It's just like a shear layer that's rolling up. And sometimes it can be hard to like say like, is this one vortex or three? Is it a colliding galaxy and it counts as one? Things like that.
But I am impressed by the capture of the detailed structure by your way of dissecting plan by plan. And that also means the flow structure repeats itself quite well over the course of the experiment.
Yeah, and on the repeatability, I'll interject here in case there's experimentalists in the audience. I'm showing phase averaged span-wise vorticity plots here, but these are very repeatable in the instantaneous. So the image I've shown here is an average of 15 pieces of PIV data. But even these like Kelvin-Helmholtz like instability vortices, they show up like in the same place at the same time in the cycle.
That's amazing.
That was kind of a result me and Dr. Green were not expecting to see. And it's also good. It's good for proving that you're like, oh, okay, these are real. They're not fake.
So Justin,
go ahead,
so
sorry.
I probably have to like stop you here. So we are like about the time. It's like 11 p.m. now. It's like I think 10 a.m. as Eastern Standard Time. So thanks everyone for coming to the IBiM talk. So Justin just gave I think it's a very inspiration talk to me at least. So I hope we can. Actually, this is the end of the fall semester. But anyway, we'll start the spring semester of the 2023 soon. I think in a month. So I hope see you everyone in a month from now. Okay.
Thank you for the invitation.
Thanks for coming. Yeah.
Thank you for all the questions.
Thanks, Justin. Thank you.
Thank you again.
Thank you.
Bye.
Bye.